All right. Greetings and welcome. Let me double check this. And great. Okay. Greetings, everyone. So today we're going to talk a little bit about array lists, just a quick review, and then we're going to go over what recursion is, because Jeff just covered that. And then we're going to use both array lists and recursion to let's print a string backwards. So yeah, let's dive into it. So let's just open up a terminal. Okay. So before we were using arrays to store lots of data. If we needed to store 10 integers or some n number of some data type, and you wanted to give them all a name and maybe their order mattered, we were using arrays. The issue with arrays is that they're not it's not easy. Oh, I mean, it's one line. It's not as easy as just when you go to insert something into an array to change its size. That an array, typically what we were doing before was we were doing something with like using a strategy called partially filled arrays, where you would make a big array and then you would populate it with the data, and you would keep track of where you've put data there, where you've put data and where you have garbage, or whatnot. So like when you go to delete something, you just change that integer to be one less, and that would essentially say that whatever's on that other side is not usable. The issue though is that every time we went to put something into a partially filled array, we would have to make sure that we weren't exceeding its size, that it wasn't full, and then we could make a new array that was a bigger array, but that requires you checking every single time of, hey, are we full? If we are full, then make the array twice as big, or whatever strategy that you're using. And for some people, that's too much code. That one line of doing the check and the one line of resizing the array and copying, and then another line of copying everything over. So 3 lines of code every time, just for checking. And so there's something called an array list that allows us to essentially not have to care about that. Somebody else has written a class that's essentially doing that behavior of, it allows us just to blindly insert things, and whenever we go to, whenever it's the internal structure is full, it behind the scenes will then go and make something that's double the size. So these are called array lists. And so the way that we make an array list is we say array list, and then we specify the type. And this has to be a class type. So one of the tricky things, so with arrays we could do primitive data types as well as classes, so classes that we've made, or classes that exist within the API. With an array list, we have to use a class. So, but we can make classes of a, we can use, just like we covered, was 2 sessions ago, where every primitive data type has a class instance of itself. So for example, instead of like a byte, there is a byte. To classes, just in general, classes should be uppercase. And so that's always a good indication that you're working with a class instead of the primitive type is the case sensitivity. But yeah, let's make a string. We're gonna make it as a string, and then we're gonna call him Sal, because he's a string array list. See, being very clever. typically you might actually type out something, whatever the context of it is. You need to really preserve that when you're making variable names. So we don't know what we're going to use Sal for yet, so that's why he doesn't have a good name. But the moment you do know what you're going to be using this array list for, you should give it a more appropriate variable name. Okay, so there we go. So we've now made a string array list called Sal. And now we can do some things. So if you recall, when we were using arrays, we would say Sal and then like square brackets and then some number. But that doesn't work with array lists because they're classes. Every time we're working with classes, we use the dot syntax. So if we wanted to say add something, we would just say dot add. And this is a method. This is a method of the ArrayList class. And it takes an argument of whatever type is here. So if you had a class type here, you could say like new string and blah, 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 blah. But in this case, we're really lazy. And so we can feed it a primitive, or I mean, strings in this case are not primitive. Strings are still a class, but we can feed in a literal string. So literal, the word literal, as opposed to how we hear it used in social media, the word literal means written exactly as it is meant to be expressed. So this here is written exactly as it is meant to be expressed. This is a string literal of yo. Okay, and bing. All right, so now Sal contains yo. And this true indicates that it did it. So now we could add something else. We could add, dog. Okay, so now Sal has yo dog, and we could say, hey, where is the index of yo? It's at 0. So we could then say like, oh, I want to say Sal dot get at 0. So this is just like using that square bracket notation, right? This is giving us at index 0 and giving it goes. So there's our yo. Cool. So that's basic array lists. And so let's add some more stuff. And we can keep feeding it things of that type. So now we should definitely be familiar, or at least able to look these up. So in the J shell, it's really useful because you can just type in Sal dot, and then it gives you all these suggestions of all of the methods that the ArrayList class has. So you could say Sal.toString, and then we get this pretty thing here. So there you go. There's just some basic array lists. So and we could make, if we made, for example, if we made a Pokemon class. So from the previous example, we would just change our string to Pokemon, and then here for Sal we would name it Pokédex, and there we go. We now have, and so yeah. So here we would put this Pokemon here and Pokemon here. Change this to Pokédex. And now you have something that can change sizes, and maybe the order doesn't matter, or that the order does matter, and that you insert them in order, but doesn't. Depending on how you're using the Pokédex, it might, you might need to preserve the order, or you might not. You notice how there's this set, right? Pokédex is going to be a set, a type set. You're not going to have duplicate entries in a Pokédex. So in the case of a set, the order doesn't quite matter. So the index doesn't matter at all. So you would be looking more at contains. So you'd be using some kind of attribute for the contains, maybe an ID or a name or something along the lines of that. And there are lots of different ways you could store a Pokédex in the background, but that's just an example that an array list, you just put in the class type here and here. Okie dokie. Yeah, so that's that's basics. Pretty much they're pretty much arrays, but they're fancier because they're able to resize without us having to be concerned about how big they are, and that they have all of these methods that make our lives easier. Right? Is empty is just like when we were doing the partially filled array. Is empty is essentially saying is, you know, if return its return size equals 0. If it is 0, it's going to be true, so it is empty. If it's false, if it's false, then it's not empty. Yeah, so all this is doing is making our lives easier and making our code a little bit more readable. But there is definitely overhead that's going to be involved, in the sense that when you create and use an array list, it's going to be a bit slower and going to take up a bit more memory than if you were just to use a typical array. Just something to be mindful. Like, I think when you just by creating an empty array list, it makes size 1,000 spots in memory. And so I had some code that did mapping on a Launchpad, one of the like, you know, those musical panels that you hit the buttons and it plays sounds. I wrote like maze solving code that would run on a Launchpad, or I mean that I could essentially use a Launchpad to display it. And wow, brain fart. Where does it go? Oh yeah, the number of directions that you could go in the maze was only size 4. And I was using ArrayLists because the array list it's a partially filled array. It can keep track of, you know, how many things there are without me having to keep checking and whatnot. And so to make my code simpler, I used an array list. The issue though is that its default was to make something of size 1,000. Now, if I was making maps or mazes that were, you know, had 900,000 nodes, and then for each of those nodes to calculate, you know, from that node which direction can I go in that maze, and I was making something of size 1,000, I very instantly ran out of memory. And so when you construct the ArrayList object, so when we construct the ArrayList object, so let's construct another one. Just we'll call him Sal2. You can give it arguments. So here we can say like 10. And so now what this does is this makes the array list and it creates it initially with this size. But what's nifty is that if for some reason we go over 10, then it will increase it dynamically. It'll go in and change the array size. But the idea being is that if you say, well, I know that throughout my program, 99% of the time, I'm never going to exceed size 10, then this is a really good thing to do. Because now you're only taking up the amount of memory that you expect to be using, as opposed to Sal, the normal Sal. Normal Sal was given a size 1,000 by default, which we're not going to, certainly in this example, we're never going to use. We're never going to hit that point. So something just to be mindful about is that array lists can get very expensive. They're take up a lot of memory, and can make your program much slower. So as a strategy is, if you know in general what your array list is going to look like size-wise, you should probably give this extra little parameter, and that's going to help out your life considerably. But the cool thing about it being an array list is that whatever number you put here, you're not married to it. You're not stuck to this number. This is just initially what it creates its size to be. Okie dokie. So there's array lists. The next on the schedule was recursion. So in order to understand recursion, and I'm really surprised Jeff didn't do this in class. We first must Google recursion. That's the joke, by the way. So notice how it's spelt exactly the same. Did you mean recursion? This is one of those Google Easter eggs, because it's a joke. The repeated application of recursion, process, or definition. So it's great. It's right here. The definition in the dictionary is recursive. It makes a reference to itself in its own definition, which is exactly what recursion is that in its definition, it calls itself. It makes a reference to itself. So that's recursion. There you go. All right. So you should be good now, right? Now let's do an example. So, recursion, Jeff showed some examples in class. Let's see, he showed the high counting, high again, and factorial and some Fibonacci. Okay, so yeah, so let's make something that counts down. So let's make a method. It's going to be of type void, and we're going to call it countdown. And it's going to take in an integer, and we're going to call it num. All right, so we need to make a base case. That's the most important thing about recursion. So the base case is going to be when we hit 0. And the question is, do we want to print out when we're doing countdown, do we want to print out 0 or not? And I don't know. Let's print out 0. So our base case will then be, to make our code a little bit cleaner, our base case will be -1. Or let's just say our base case is negative. That way our code is much more robust. So if we say if num is smaller than 0, return. And there we go. There's our base case. So essentially, if countdown gets called, and num is smaller than 0, we're not going to do anything. Okay. Now let's do some stuff. So now we're going to call the printout system.out.println num. All right. Okay. So right now it's not recursive yet. At this point, if somebody gives us a negative number, we don't do anything. If we get a 0 or a positive number, I don't know, it's debatable whether or not 0 is a positive number. But if we get 0 or any positive number, we will print out the number, and then that's it. Then we're done. But we need to make this recursive because this is a recursive example. So what we're going to do is we're going to call countdown, and as an argument to countdown, we're going to say num -1. Cool. Okay. Oh, I have power notifications. Okay. All right. So let's call countdown. And then we're going to call it with the number 7. And there we go. 7, 6, 5, 4, 3, 2, 1, 0. So there's our code for countdown. Now let's do something that's really, really cool. We're going to not change any code. We're going to swap the order of 2 lines. You know, let's move this to a text document so that you can see what's going on. Okay. Come on. Hello. Oh, whatever. Oh, that's fun. I can't zoom in for you. Huh. Not sure. Let's just increase the font size. Okay. All right, so all we're going to do here, so literally copy pasta, and it's going to be count up, and all we're going to do is change the order. This goes there, and that's it. So all we did was swap 2 lines. And now we're going to call count up. So notice count down, counts down, count up, counts up. But notice one of them's out of order. And so a fun thought to go through is, where does this one come from, right? Where does this 7 come from? Well, it's the first one, but it has to wait until all of these are done before it will print out. So it's just something fun to think about. This may blow your mind, the fact that we just swapped 2 lines and it pretty much reversed the behavior except for this one case here. So this, I would highly recommend tracing out on some paper, because this is a really, really important part of recursion. And let's see. Just trying to think of something. Okay, let me take a quick break and I'll be right back. All right. Okay. Just make a comment. All right. Just a note to ourselves. Okie dokie. So that's recursion in general. And in this case, we could just write this as a loop. as a like a while loop or something like that, or a for loop. That recursion is really not necessary to count up or count down, right? I mean, we could very easily just say like for int I, and then we could say like as long as I is smaller than num, we could say num plus or I plus plus, and then here we just print out our num, right? There we go. We've now int num equals 6, and there we go. Oh, yes. Getting lazy. Okay, so there we go. And actually, oh, we're printing out num. We want to print out I. So there we go. And notice that we're omitting that one. So if we wanted to include that one, we would just say equals. So no need for recursion here. And then if we wanted to flip it, we could just say we could start it at num. So if I want to count down, and then I can say as long as I is greater than 0, I minus minus. Oh, and then if I want 0 equal. So there we go. There's our count down. So count up, count down. And so let's just throw that in our handy dandy text. So this is count up, and then our count down. Right. So there you go. So there's no need for recursion for these basic operations. You can just use a for loop, but recursion is an incredibly important thing to be able to grapple. And so for now, it's important to be able to recognize when you see recursion, and essentially if a method calls itself, that's a dead giveaway that that's recursion. And if you see it calling itself twice, that is also very much recursion. There are lots of strategies called divide and conquer. A lot of sorting algorithms use it, that it will essentially split the data in half, like whatever data it's given, it will split the data that it's been given in half and then sort it again. And that's called quicksort. Quicksort, that's what it does, is that it essentially calls sort on, it splits the data in half and then calls itself on those two halves. And dividing and conquering is very, very efficient because, well, not only because you're breaking up the task into smaller and smaller pieces, but also because we have all of these computers have tons and tons of threads. They have the cores. Originally, computers used to be single threaded, where all of your code ran one thing at a time. And so far, all of the code that we've written, and like 99.9% of the code that we're going to write in this class, is going to be single threaded. Maybe towards the end we might write something that isn't single threaded. But right now, all of our code essentially executes one line at a time. But in the future, when you go into the real world, your code will be running multiple lines simultaneously. So for example, this here, you could essentially stick this line and say, hey, whenever convenient, do this code. And then, hey, whenever convenient, do this code. And what could happen is that on one processor, it's running this code, and on another processor, it's running this code. And we see this happening, I mean, hopefully everywhere. If you're running everything in a single thread in the real world, like for real business applications or real science research, you're going to be in a whole lot of hurt. The code needs to be able to be written in a way that you can split up the task and hand it off to people. So distributed computing is very important. I'm sure that you've heard of this Bitcoin thing, right? The ability to be able to split up lots of tasks to all of these computers all over the world is really important. Not just because of some silly e-commerce that doesn't really have any value, but for example, let's look at Stanford. Stanford has cancer research that is entirely done based on people volunteering their computers. My computer downloads a payload from their server that then says, hey, go do some number crunching. My computer works on it for 2 days or so, comes up with some protein solution that says, yeah, this protein looks really good, like it's effective for against cancer. And then that gets turned back in to their servers, and then they're able to tell the researcher, hey, yeah, this the cluster of computers that was distributed, that the load was shared with, was able to come up with a solution, or was able to verify that yes, in fact, this protein interacts with this cancer cell in this way. Or they could also be looking at side effects, saying, hey, this chemical has been shown to be very effective against cancer, but how does it behave with all of the other cells in the human body that we have models for, and being able to test for that. So being able to think in a recursive way of being able to split up your tasks into lots of little individual calls is really, really important. Because it allows you to break up your tasks and do this sort of load balancing. When you go to google.com, google.com isn't one computer, it's not one server. When you request their website, just the act of requesting the address to the website, there are hundreds of servers that just respond to the request to find the address of the website. And that just a request of the address of Google. So when you type in google.com, that name has to be resolved to a number. And there are thousands of things that resolve that to some number to say, hey, go ask this person for another number. And then there are hundreds, if not thousands, of those systems. And then those systems would give us an address of saying, yeah, go talk to this specific server, and they will then give you the Google home page. And so the idea being is that you're in this mode of being able to break up a bigger problem, like your code for a search engine, into lots of little individual methods, and that they all connect in a way to each other that allows them to be very seamless. But when I call the countdown, let's go back up. When you call countdown 7, that maybe this 7 and this 5 were run on different threads or different processors, or in the case of like the robots that I work with, the code could be running on a separate computer, like in a separate spot, one could be using a battery, and the other one, that's somewhere remotely, and the other one could be a giant supercomputer somewhere. That from one call to the next call, it doesn't matter where it's run or who's running it. If the code is written in a way that everyone can run it separately, independently of each other, then you have some really good code. So that's just something to think about right now, the recursion that we've been shown is not particularly useful for solving these cancer problems and things like that, but that this is the strategy, and being able to look at this and identify and recognize it and get used to it. Recursion, you have to have a base case, and somewhere in the method or the code, you're going to be calling yourself. Those are the two things, the two takeaways. That way, when you see recursion, or you're expected to write something that is recursive when in work or even in class, that you're not totally lost, that you have a fairly good idea of what's going on. And that when we flip the orders of when we do whatever work, whatever action, whatever processing that's going to occur, that just changing when you recurse and when you do work, that will change the order in which they occur. Just flipping these two, that they essentially flip the code. Okay, so that's the basics of recursion. Let's take a look at Sal again. So let's print Sal forwards. Oh no, let's just print Sal backwards, right? So let's print out, this is a test doggio, and let's use recursion. So we're going to make a method, and let's just type it out here. That way we have syntax highlighting, and it looks pretty. So it's going to be void, and then we're going to say we're going to consume things of this type. Oh, and we're going to say print backwards. And so we're going to take that guy, and we're going to take in an argument that is going to be the index. And let's give him a name. Let's call it text. Okay. All right. And I got 13. Okay. So we are going to essentially say, I'm trying to remember, is it at or get? Oh, it's get. Okay. So we're going to say text.get at index. So the first thing to do is write our base case. So if index is, and remember, index starts at 0, so we need to include 0. So if index is smaller than 0, then we return. There we go. There's our base case. Now we want to print stuff out. So we're going to say this guy. I don't trust myself to type. Okay. And we're going to also recurse. So far, right, we haven't written anything to indicate which direction we're going besides saying backwards. So we're going to call print backwards, and we're going to feed it in text, and we're going to feed it in index, but that is going to be index -1. Okay. All right. And that should be it. All right. So now if we call print backwards and we feed it Sal, and we feed it Sal dot, was it size or is it length? Size. And out of bounds, index check. Yes, -1. See, size, if you have one thing in it, size is going to tell you 1, but we need it to tell us 0 because we're using it as the index. So in order to convert a size to an index of the last element, you just subtract 1. And there we go. This is a test geodog. And if we recall, cell looks like this. Let me pull this guy back up. So there you go. That's how you print backwards. This is a test doggo. This is a test doggo. So success. We have now written something that will then process, print backwards. And if we wanted to remove these new lines and just put spaces instead, we could just make this print, and then we could make, and we might use a printf to do this, but we could just say print and then add a space. There you go. So this, if you made this a printf, you could make this one, you could make that this one line. But yeah, so that would remove this new line and make it a sentence to print it backwards. But there you go. That's ArrayLists and Recursion at the same time. Hopefully that was useful. If you have any questions, feel free to email me or message on Slack or post something in on the website. All right, good luck.